Good morning, good afternoon, good evening, wherever you are joining us from. My name is Michael Watson and I lead our reactor program in the Asia Pacific. And today we are delivering our session for the Reactor APAC, our virtual reactor where we are showcasing the wonderful talents across the Southeast Asian region. And so we are today very fortunate to be joined by Ujjwal, who is a senior architect within the Microsoft Technology Center based in Singapore. And today's session, we're going to be running through a lot of the stuff around Azure Quantum and industry case studies to support that. So Ujjwal is as I said, he's been with Microsoft Technology Center. We've been with Microsoft for 15 plus years and has close to 19 years of technical and pre-sales experience in various industry domains and technologies from Azure apps, infrastructure, blockchain, IoT, quantum computing, you name it, he's got it. So you're very fortunate to have a wonderful speaker like this today. And on the academic front, he also holds a master's in technology and in IT and leadership from the National University of Singapore, and has studied quantum computing from MIT and other places around the world. So an incredibly diverse speaker, well-rounded, and a number of qualifications to support that. So what we will do is we'll kick off in a second. I do encourage you to please ask questions. Use the comments section if you have questions. We will get to those during the session, or if we have time at the end, we'll navigate that as we go. And please enjoy the session. This will be recorded and it will feature on our YouTube channel at the end. So without further ado, I will now hand over to Ujjwal and I will show his presentation. So thank you very much.
Thank you, Michael, and thanks for the kind introduction and the opportunity to speak today at the reactor about Azure Quantum and industry use cases. So thanks for the introduction as well. I just wanted to very quickly mention that quantum computing, to get started, is the future in which we are moving away from binary computing to something very different. Right? We are potentially redefining how we think about computing, and for looking at how we are thinking about the toughest computing challenges. So today, I'll be getting to walk you through about the concepts, some of the scenarios, and also about what we are doing from Microsoft side and what offers we have from Azure Quantum side. And then we will also go through some of the industry use cases. I mean, there are many of them, but I'll just walk through some of them today. But I'll also leave with resources links, and that's something people who are watching this now or in future would be able to leverage to learn more about it. And without much ado, I wanted to play a very quick video. It's very interesting to show you where we are and where we're moving for quantum.
Houston, we see you. We have a go. Over.
When we talk about quantum computing, it's a completely different game.
Quantum computing will enable us to solve problems that currently take longer than the lifetime of the universe in seconds, hours, or days.
We completely reconceive the space in which we do computation.
Quantum computing is like going from crawling to going to a different planet. It's different.
It's only natural that we would want to use the world's most powerful device to combat the world's most challenging problems.
We could attack global warming.
Security.
What are the boundaries of machine learning?
Fighting diseases. The possibilities of quantum computers are endless. Microsoft has the best and the brightest working on this problem.
It's really happening. Progress is very fast. And we're building a quantum computer.
What the world wants to know is what happens when we turn the machine on.
What problems will be solvable with a computer that computes in a billion parallel universes at the same time?
Well, just now you saw the video and it's very interesting. So just to summarize this, right, why we should be caring about quantum computing now and thinking about it, because despite all the advancements we have made in the compute world and the power of the cloud, there are still problems which remain that we are not able to solve, even with all this compute power. And problems which are some of the problems which you just saw in the video and top of my mind as well, for example, is climate change, the natural resources, how we optimize them, and also evolving our modes of transportation, for example, right, in this ever growing gridlock population. And especially when we talk about countries like India, China, and where we have huge amount of population, that kind of scenarios of having optimization for routing is huge. And I'll be showing later today. I'll in fact walk you through some of the examples of where the quantum inspired optimization has actually been able to work on some of these problems even today, right? So quantum is redefining the meaning of computing to address planet scale challenges. And at Microsoft, we are building, some of these tools. We are also going through the capabilities to go often after these challenges, like I just mentioned. Now, as we go along with this scenarios, we are also looking to bring out an open ecosystem with Azure Quantum, and that not only puts Microsoft technology at your fingertips, but also a community of quantum hardware and solution providers as well. So I will be going through in the next few slides about it. But before that, I actually wanted to jump through and give you a quick perspective about why quantum is so exciting. So if you notice this slide here, right, I just wanted to look at some of the problems, that is tough computational chemistry, for example, right? Computational chemistry is very interesting because at this we are looking at molecules at larger scenario, right? And primarily what we are looking at is as we go along in the periodic table, as you could see here in the red line, primarily this one, the scaling of the classical compute algorithm needs to be at exponential for solving the molecule complexity, which is not really available today. I mean, in the sense that there is a limitation of how we can use classical compute in an exponential way, because it's always going to be n square, where n is the number of bits, and it's always going to be to the power square, right? But in the sense of quantum compute, it's something which can help us build or think about solutions in an exponential mechanism, or in the sense that we are able to solve something in a way where we have multiple ways. And the example could be that when we have an n number of qubits, it's going to be 2 to the power n options for us to think about that kind of problem, right? Is always going to be exponential. And that's where we see that even with the parallel compute evolution, right, in the classical scenario, we are just able to move this red line to a little bit towards the right, but still not linear. Where in compared to the curve with the quantum computing side, as we grow, right, and as we are thinking about these challenges, with the improvements, the quantum computing, because it operates in a different principle, right, than classical compute. For example, when we talk about it works in a native language of nature, right? For example, it is based on quantum mechanics, and it mimics the reactions, the designs, and the process of nature, right? So we are able to calculate some of these complex equations very accurately, predicting, for example, catalytic properties of a chemical compound, and that helps us to move this kind of curve to more linear, right? I mean, it's definitely not completely linear, but at the same point of time, there is a big improvement in terms of how we are able to move towards solving some of these tough, challenging problems. So what makes quantum computing so different, right? In the sense that we will run through a quick introduction view now. I will just walk you through some of the examples of the building blocks of quantum computing. And to do this, let's look at parallel with the classical compute, right? So if you pop open a device and look at the transistor inside, you will find that there are switches, tiny switches, which can be turned on and off like this, right? And that they can support one state at a time, on or off, right? And we map these on and off to ones and zeros. I'm sure most of you already know about this. Now, the more information and the compute power we need, the more ones and zeros we need, right? Therefore, more transistors we need. Now, which is why we strive to fit more and more transistors on one single chip, and increase the size of the chip has been decreasing, actually, right? So we have sizes now which we can't even see with our eyes, right? It has gone to almost something at a size which we need to use a microscope to see those kind of transistors. Just to give a perspective to this, right, we have gone from a computer which comprises about 13,000 transistors to the size of a room, to fit in 13,000 transistors fit in a big, large room in the 1960s, to a gaming console like Xbox, which comprise of 5 billion transistors, and it's this big size, right? So you can imagine that we have gone through a long way in the classical compute. But at the same point of time, we are not there. I mean, in the sense that we always need more and more of this to solve the problems in challenging problems in nature, and that's where classical compute is still facing some of those issues in terms of representing and solving those problems at the same point of time. And I'll talk about that in more detail later when we compare the two. But let's look at the fundamental building block of a quantum compute. So on the quantum compute side, on the other hand, right, it can have more than one state at any given point of time. So it can be at a 0, it can be at a 1, and simultaneously it can be at any state between 0 and 1. And this is what we call as superposition, right? So essentially, what it means is that we can let's take an example first, right? I mean, to understand this in why this is so powerful, right? Let's take an example of the classical picture again. I wanted to show you here, we have 4 bits of registers, right, as you could see in here. But this register can only have one combination at any given point of time, right? So it could be either 0110 or 1010 and so on. So it means that while we have 4 bits, we would be able to have 4 squares, so 16 scenarios. But those 16 scenarios, we can only pick one at any given point of time, right? Now, when we are looking at a quantum bit or a qubit, in this case, this is very different because each bit can be programmed to be in a superposition, which is 0 or 1 or any state in between, right? Which we can encode into a classical information in this register as a linear superposition of 16 combinations and compute them in superposition. So what it means is that I can actually have 16 state. So it's still 16 because it will be 2 to power n, and in this case, it still goes to 16. But then as the number grow, it will be completely different. So I'll talk about that. But just be mindful here what I'm trying to bring, why it is so powerful. At this any given state of time, we actually can have 16 states, right, or scenarios, right, which is very, very interesting because this is exactly why it makes it so powerful. Now, look at the scenario, right? So in case of classical compute, we would need parallel mechanism, right, to actually achieve that, wherein the 4 qubit itself is good enough, right, because the quantum computer is exponentially more powerful. And this is the benefit or big benefit I would talk about. I mean, there are, of course, low points as well, which I like to highlight later. But at the same point of time, as we continue on this course, every time we add a qubit, right, we double the amount of information we can encode. And it's very inherent nature of qubits that gives us this opportunity of massive speed ups in the computation, right? Now, let's look at how we can put this in some context, right? So with the quantum computing, we can achieve an exponential increase in the compute power, obtaining double the power with each additional qubit, right? So if you want to simulate a quantum computer on a classical compute, this is an example. So if I want to simulate about 20 qubits, I would need 16 megabyte of RAM. But if I want to simulate, let's say, 30 qubits, I would need 16 gigabyte of RAM, right? Wherein actually I can still simulate on my machine today on a surface on which I have 32 GB RAM, because it requires additional memory, for example, to run the operating system itself and so on, right? So I would still need some extra capacity. But at the same point of time, since I have 32 GB, I can spare 16 GB separately, and I can actually simulate about 30 qubits on my local machine. But now think about this. For me to simulate 40 or 50 qubits, so 40 qubit would be 10 times, not more, not just 10 times, it will be more than 1,000 times memory. So 40 qubit would require 16 terabyte, and as you could see on the screen, 50 qubits require 15 petabyte. So it grows exponentially higher, right? And it's continuing to grow, and that's where a classical compute, which is available today, may not meet this kind of requirement in a longer term. And that's where we are actually in the industry, a lot of work going on in terms of generating a qubit, quantum bit with different mechanisms, and I'll talk about that: superconducting, ion trap, and Microsoft. We are also building our own, so I'll explain some of those scenarios and the different types of mechanisms which we are using to build that. Now, I wanted to also highlight one important aspect. Now, quantum, as it sounds, and so far I've talked about, seems to be super impressive, but at the same time, it may not be good for solving all hard computational problems, right? We need to develop algorithms that can leverage the quantum principles like superposition I just talked about, or there are other principles which I haven't talked, but it will be things like quantum interference, and for those scenarios, we really need to look at examples, right? And today, some of the examples which I'm putting across, right, so is based on the research and the experiments which has been done so far. What we have found is quantum computing promises to disrupt large, complex problems across these 4 key areas which I've been highlighting on the screen now: cryptography, right, optimization, the simulation of quantum systems, and potentially machine learning. I mean, this is a new area which has been emerging over a period of time. What we have seen is there are a lot of solutions coming up, and a new field has emerged called quantum machine learning around it as well. So it's very interesting to look upon. Now, solution to these problems, has been very interesting in the areas to help challenges around sustainability, climate change, food scarcity, medical diagnosis, transportation, logistics, and in financial segments, for example, risk modeling, and much more. And I'll talk about some of those as we go along today. Right now, as we look into some of these areas, the amount of disruption which comes in proportion to the amount of data required to solve the problem, right? And that's because quantum computers are great at computing, but they're not really great at reading and writing large amount of data, right? So just to give you a quick example, think about RSA. Now, RSA algorithm in cryptography, we use that very often, right? And breaking an RSA requires taking a large number, right, and identifying two prime factors that are multiplied together to get that number. Now, if we look at the input data, if it is one large number, right, the output will be just one small prime number, right, in terms of RSA computation now. But the compute required is large, and you must be going through multiple instances to find the right factor to be able to solve that. And quantum computer does this very well, so but solving problems in quantum with quantum in cryptography may not yield commercial value right away, right? So in contrast to that, machine learning, for example, right, these method requires a lot of data, and the models are now in millions to billions of parameters. So this is huge, right? This is large, and it will take an incredible large quantum computer to show commercial value in machine learning. So while machine learning is very promising, it will take time to get that yield or the value, right, in this area for some, unless we develop like more and more qubits which could hold that kind of data and work with that big data, which is work in progress, I would say. So coming back to the sweet spot, right, for quantum computing, where we can outperform the classical solutions and achieve practical and commercial value today, right, is around optimization and is around simulation of physical systems. And in addition to that, we can also take some quantum mechanical techniques which we learn from quantum algorithm and emulate them on classical hardware, enabling to achieve some speed ups today, right? And we call these quantum inspired methods. So for example, to empower our customers and with this quantum computing, what we need is two things, right? We need services and solutions available at fingertip, right? And also we need a quantum computer that can scale to thousands to millions of qubits and beyond, right? And this is where we are working on a system which is called topological quantum system, which are co-developed and co-designed across the hardware and software components from Microsoft side, right? And we are, let me explain that in more detail as we go along. So, but before that, I wanted to very quickly give you a view of where we are, right? So I talked about qubit, and I talked about like qubits are the building blocks in terms of quantum, but it's not the only element that is required to reach the level of scale and to have an impact, for some of these key problems which we have been talking about. So solving these planet scale problems requires, us to build and scale the entire quantum stack, from the quantum hardware, as you could see in the picture, to the classical control systems, programming models, and also the frameworks to the application layer and services and solutions. And there are advantages to developing all of these layers in the stack, right, in parallel. As I've been mentioning about, like our depth of understanding in algorithms and applications is deeply informing that the hardware is aligned, and we are building that together from Microsoft perspective. Right now, important aspect I wanted to highlight here is the fragile nature of qubit. So far, I've been mentioning that qubits are great and very powerful, but then there is this interesting fragile nature of qubit, which is that the basic unit of quantum computer, right, is well known for one of its most significant hurdle in terms of producing the scalable system, which is because of the slightest interference, the state of qubit can decohere or collapse, right? And that's where Microsoft is addressing that fundamental challenge by building this revolutionary topological qubit. Topology essentially means, or rather, I would say it refers to the properties that are insensitive to deformation in local geometry. And in case of qubits, right, this means resistance to errors and interferences. And topological protection in our qubit, right, essentially intrinsically protects the qubit from many sources of errors. And this means that the qubits stay in quantum state much longer, enabling us to do more quantum computations before we lose that information, right? And this protection reduces our need for error correction and also enabling us to reduce the size of the logical qubit, right, which enables us to scale to millions of qubits required for commercial applications, right? And basically, it helps us enabling in building this large scalable quantum computer. So this is work in progress right now. But while I was mentioning this, I also wanted to highlight that there are already quantum computers available from our partners and also from the global ecosystem as well, right? So there are multiple large organizations like IBM, Google, who have built their own physical quantum computers, and we also have partners like Honeywell, INQ, who has also made their physical quantum computer available. And let me highlight what we are doing today with them, right? So when we talk about Microsoft and Azure Quantum, there are three different horizons. So we are currently in Horizon 1, moving towards Horizon 2, where we have extended our classical compute. So we provide simulation. As I was highlighting in the previous slide, that we need about 40 terabyte for 16 terabyte for 14 qubit, 40 qubits, right? So we provide that kind of simulation environment through Azure. So using Azure Quantum, you get that simulation. We are also building a large ecosystem, and we also have early partnering with physical quantum hardware providers like Honeywell and INQ and QCI. So essentially, what it means is that you today have access to physical quantum as well as simulation through Azure, and we are building this large ecosystem so of hardware, not only hardware vendors but also software vendors and providers who have specialized in this area and have libraries being made available. Our own research team at Microsoft is also building this libraries to enable the developers take advantage and focus on their algorithms and the product rather than building the libraries from scratch. For example, in computational chemistry, we have published some of those libraries which people can directly leverage and start working on and focusing in their environment, right? While we are doing that, there's also a complete focus in terms of moving towards Horizon 2, where we are continuing to work on the current state, but at the same point of time, leveraging the migration of scenarios for the future quantum workloads. We are also looking at the new advancements that our partners are making in the hardware, and we are looking to bring that up. For example, in future, potentially when the more amount of qubits are available, possibly that would be coming back into through Azure access by anyone who wants to access the quantum computer, would be leveraging that advancement our partners are making. And also the Microsoft topological quantum computing, which is in progress, hopefully would be featuring in Horizon 2 as well. Horizon 3 is where we are looking at building or helping out those commercial application acceleration, right? So essentially, there is already a program from Microsoft product team in the quantum team available today, and those programs, for example, SI system integrator program or early access program for customers available today, which can help the SIs or the customers start building applications, through partnership and so on. But at the same point of time, we are also going to be publishing more libraries for people to actually get started quickly and build applications. And we are, of course, looking to unlock the optimization chemistry and the material sciences through this hybrid classical quantum solutions as well. So these are the solutions that are required to have the scaled quantum hardware for acceleration, and these are then accelerated for our unique first party quantum system as well. So while I'm at it, I actually wanted to also mention why we should look at Azure Quantum, right? um, if you're learning quantum or developing quantum algorithm or applications or applying quantum, you may think about Azure Quantum. And my core motivation, and I would rather say our, from a Microsoft perspective, our core motivation from the inception has been to build a large ecosystem where all parties can benefit, right? And this is what really is driving Microsoft in this quantum investment, especially for the customers. We offer unified access to the latest hardware, right? And if I can think about, people can think of this, uh, for granted. For example, when you look at traditional silicon, right, most of the part I can write a program once and then deploy that, and I could run on Intel or AMD. However, if I have to switch and run the same program on ARM variant, I have to rewrite a lot of part of the code to be able to do that. But in with Azure Quantum, what we do is we are bringing you a level of abstraction that simply nobody else is able to provide today, right? And what it means is that you could write a program targeting any piece of hardware, right? It could be a quantum computer built using, let's say, ion trap mechanism, and with two simple lines of code. And I'll later show you a demonstration about it. With very few lines of code, like essentially two line change in the code, you would be able to retarget to, let's say, a superconducting based quantum computer, or maybe in future topological quantum computer when it comes, right? So the idea is, and you could also target the simulation, the simulated environment, to run it on a local machine. So what it means is that you're getting this huge benefit of focusing on the problem rather than focusing on the target platform, and have a truly scalable system coming in place. At the same point of time, when we think about the developing ecosystem, right, and Azure Quantum has been focused on that. So we are really working on an open ecosystem. And essentially, Azure Quantum brings this language called Q Sharp, and the Quantum Development Kit, which are open source already, are available to the broader quantum computing. Q Sharp essentially is a universal language, meaning it can run not only gate-based quantum computers. In fact, it can run all types of gate-based quantum computer, right? So that's what I was trying to mention. And also it brings in the most diverse and robust set of hardware, I would rather say, and software and the solution partners all together to be able to build solutions. So some of the examples, and I'll show you some of the partners in our list, are from IonQ, Honeywell, QCI to 1QBit and Toshiba, and so on, where we are, and then there are many others. Even in this part of the world, there is Singapore-based quantum-focused compute company, which is Cureka. There are many others who are available today, working towards partnership. So there's a quantum network which is available, and organizations who are interested can join that as well. Now, over a period of time, Microsoft will also bring in topological qubit-based hardware to Azure Quantum, making it one-stop shop, for now and into the future. Having said that, we also announced very interestingly the partnership, like basically the ability to run Qiskit based solutions. So for example, we know that it's a large community of developers leveraging Qiskit, or for example, and those two programming languages has been incorporated. So with the Azure Quantum as well. What it means is that developers who are writing code with Qiskit or Circ could also leverage Azure Quantum and write their applications and test it out on Azure. And we are focusing on the impact today, right? Essentially, there is this, as I've been highlighting in the beginning, that quantum computing is not best at solving all types of problems, but and then there's also area of focus which we can leverage today. And this is where we are bringing that kind of familiarity, Azure familiarity and scalability of the world's computer to quantum computing, right? Essentially providing quantum tools and capabilities to make it easy for you to get started as well. So very quickly, I wanted to jump further and talk about the capabilities before I can show you some demo as well about this. So the big advantage is that you can use the same tools. So you could use Visual Studio Code or Visual Studio itself, right? For example, and again, Visual Studio Code you could download for free. There's no license required separately to buy. And then at the same point of time, the programming language Q# is open source, right? Essentially, it's an open ecosystem. And as I was talking about that, quantum Q# is a universal language, meaning you could run on any gate-based quantum system, right? At the same point of time, Azure Quantum brings the world's most diverse and robust set of hardware and software and solution partners as well, right? So one of the other thing is about programs we are running. So one of this is Enterprise Acceleration Program, where it's a nomination-based process, and you could apply for a specific problem set you are trying to solve. And if that is true, there are a lot of benefits in terms of working directly with the product team members, as well as leveraging certain benefits working in those areas working together. It's a paid program, but at the same point of time, there is SI program, and then at the same point of time, there are also a lot of resources published in the open source world, with GitHub being the forefront. We have been publishing some of these libraries and solutions on GitHub as well. There are learning tools like Quantum Katas, which are available to you, and we have also published a learning site, microsoft.com/learn, and there are more than 7 hours plus content to get started on quantum computing with Q# as well. Now, going back to a very quick example of our quantum partnership, and this is one of the scenarios where we have this Honeywell, IonQ, and QCI from a physical quantum compute provider perspective. At the same point of time, IonQ also has a simulation environment available to you. 1QBit, Microsoft ourselves has quantum-inspired optimization, and Toshiba. Now, this is not the only list we have. It's a huge, big list. We have multiple other set of partners and vendors available to incorporate, and I'll be sharing that a little later as well. But having said that, let me very quickly give you a view about detail to the two different paths we have today, right? So Azure Quantum, application fall into two categories: optimization and then quantum computing. And on the left-hand side, when you see optimization, basically it enables you to solve difficult optimization problems, as name suggests, right? Or on a classical hardware using algorithms which are inspired by physical processes. And to take advantage of quantum inspired in Azure Quantum, you would use our Python optimization SDK to submit problems to Azure Quantum Optimization Service, and then get a result out of it. In a classical scenario, we have a converter or a code which basically converts the classical inputs to a quantum, and then once the solution comes out, or the output is coming out, that will again be converted back into classical, so you can consume that in a classical units. At the same point of time, the Azure Quantum Development Kit contains when we talk about Q sharp, right, and Q sharp is for applications using leveraging quantum computer, and it, which could run on not only quantum computer, physical quantum computer, but also on simulations, right? And there is also a quantum development kit I've been highlighting and talking about. Now, this kit contains all the tools necessary to develop quantum applications for both for optimization as well as for the quantum computing. So primarily, if we focus on open source tools for quantum execution, so Q sharp includes the quantum development kit, right, which is programming language designed specifically for quantum applications. And the QDK also includes, quantum development kit essentially includes the tools which helps you get started with quantum computing or execution easily. We also, as highlighted, that there's a quantum kata tutorials published on GitHub, and code samples and IDE integrations are available. So, for example, in Visual Studio Code, there's an extension for Q sharp, which will actually get you very quickly get started with the functionality perspective, or domain-specific libraries on the application is available on GitHub as well. So now I wanted to double-click on the Q sharp part I was talking about, right? Specifically, the language itself is designed specifically for developing applications for quantum computers. And the nature of quantum computer is built directly into this language, right? Enhanced with additional libraries and high-level functionality specific to quantum applications. So, for example, qubit is a Q-sharp data type, right? It's a built-in data type, which means that quantum concepts like superposition, entanglement, measurement can all be modeled through implicit side effects very nicely. You can think of Q-sharp programs as a classical program, right, that can send quantum instructions to a quantum device, and then those quantum device can help you accelerate for your classical workload application, right? So having been designed in this way, specifically with quantum execution workflow in mind, Q-sharp enables us to have this kind of automation for many classical tasks you want to leverage and is needed to make good use of quantum computers, right? As an example of this would be inverting sequence of instructions, right? A common occurrence in quantum computer where Q-sharp has built-in within functionality, right, to automate this set of classical instructions so you can focus on developing algorithm, right? And that's very interesting so to think about. So without much ado, what I would want to do is quickly highlight. So again, this is not the complete list. We have ever-growing partner list, as well as we are actually working with a lot of universities across the globe. You could see some of them here as a curriculum and research partner. And we also have a growing list of our customers and partners in this scenario. So what I'm going to do next is to actually walk you through a quick demonstration, right, of how you could use with Azure Quantum. So let's look at this in a scenario. It is very similar to the Azure services you must have used in the past, right? So basically, you notice that this is same Azure portal environment, and there is this set of resources, available to you, which you could use to basically start leveraging on. So there is a workspace, right? So first of all, you type in Azure Quantum, and you'll get the workspace. Now, in this workspace, you would be able to provide a resource group name and then the instance name itself, what region you want to select. So, for example, East US in this case. And then we provide the storage name where you would be storing your classical information. And then you could see that there are different providers available to you. So 1QBit, IonQ, Honeywell. And then you also get to see the terminology sheet. So from Azure side, we have Microsoft side, Microsoft Quantum Inspired Optimization. And then other partners you could select as well, right? So I've selected, for example, some of these, and then we could go ahead and create. Now, the advantage of this is that once you have created, right, you can is very similar to any other resource for that matter, and then you could use this to connect to the system. So here I'm taking an example. I'm going to use this Visual Studio Code to look at the problem of weights of a cargo ship. This is a critical issue in maritime transportation scenario, right? Where we getting this Python program that defines the problems and targets the quantum-inspired solver, right? So within the program, I can optimize a problem against multiple targets, which allows me to compare the result and also look at the performance. So once I create a function that defines this problem, represent weight of different containers, I can submit the optimization problem with just 2 lines of code, right? Essentially, one is to select the type of solver where I would specify the workspace, and then second one is to term the solver itself. So here I'm putting in the solver to optimize, and then I would be able to execute this, right, with a simple 1 qubit, for example, in this case. And I could change this with 1 line of code, right? With once I've executed this, I could change this to our partner, as I was saying, 1 qubit, and we could see the solution as well from there, right? So essentially, the idea is that with minimal line of code of change, you're able to run through. Now, what I wanted to do is prepare for Bernstein-Vazirani problem. Now, this is a very interesting problem which was invented in 1992. It's about one of the earliest instructions to showcase that quantum computing had advantage over performance. It can outperform the classical computer. Now, the algorithm itself is to find the unknown length of an unknown string in just 2 queries. Essentially, this can be done in a classical computer where you would need to run n+1 queries, where n is the length of the string, right? Where in using this algorithm, you could, with quantum or quantum-inspired scenario, you could basically be able to find the length in just 2 queries, right? So in Q# program, first we start with the entry point, as you could see here, right? And then we specify the target. No need to change any source code, right? You can use the Azure CLI, or you only need to specify Azure Quantum group, and the workspace which you have used with all the subsequent commands. I'm just playing here. Now, once we are done with building the project, we are going to submit the command to specify IonQ simulator, as you could see here. Now, there are 3 important commands here, right? We are going to use submit, which is to run the program against the target, show to query the execution status, and output to see the result, right? So here, the first thing, submit, done, right? Then we could see the output coming in. So show, and then the output to see the result, right? So essentially what we are doing here is to, after verifying this program subsequently with IonQ simulator, I could actually change this code to actual quantum hardware. And in this instance, we are going to be, I'm going to be leveraging Azure Quantum IonQ processing unit, or a QPU for short, right? So you see here the QPU part, and then now it is coming in. Finally, I can see the output as I've previously done here, right? So to summarize this, Azure Quantum allows you to work in an environment that you already are used to, and trust Azure Portal, which you have already been using as well to manage Azure resources. And then the command line interface is simple to run all the and manage your jobs. And then from a tooling perspective, you have Visual Studio Code, and Jupyter Notebook to write your own code as well. So with that, I'll move next, and talk about very quickly about quantum optimization, and especially quantum-inspired optimization, rather. So since we have seen a quick demonstration about this, and I wanted to jump into use cases now. One of the main use cases is around optimization, and that is where quantum-inspired optimization sits really well, right? So while I've been talking about quantum-inspired optimization, let me go through it now, right? So essentially, when we talk about this term optimization, what it really is, it's a simple, relatively self-explanatory term, right? And it falls into a category where it applies to a large range of problems as well, right? At its simplest, when you talk optimization, it is about a process of selecting the best thing from a set of possible options, right? So there could be many, for example, scenarios, and we are looking to find the best scenario. Now, the best could be defined in many ways, right? It could be the option with the lowest cost, or the quickest runtime, or maybe the lowest environmental impact, right? To speed things up, we usually just generically refer to this definition of best as a cost, right, to be minimized. If we wanted to maximize the cost instead, for example, we wanted to maximize energy output, right, for a solar cell, then all we need to do is multiply the cost by -1 and then minimize it, right? So it is both options are available to you very nicely. So now usually when we say we have an optimization problem, what we mean is that we have a pretty complicated one, right? Where there are lots of variables which can interact in many ways to influence the final cost. We call a particular arrangement, right, of the variables the configuration of the problem. And because there are many possible configurations to choose from, it gets really hard for us to identify the best problem, right? Particularly when the problem space is really large, and it can be very easy to get stuck in a local optimum, like we can see here in the graph, right? So the way the cost varies as a function of these different configurations gives us the what we call the cost function, the line of this graph, right? So let's move next. I wanted to quickly jump into the Azure Quantum part here, right? So in Azure Quantum is really unique, right? As I was mentioning here, that first we are offering a marketplace of solutions. From one service, you are able to select the solution that is the best applicable, cost effective to your problem. Second, internally at Microsoft, we are also building, on 20 years of research, 20 plus years rather, right? And I have been going through this rare expertise of optimization inspired by quantum techniques, right? So we have recognized that not one solution will fit all, and that's why we are combining traditional optimization algorithms alongside with these quantum inspired techniques. So alongside Microsoft, we also have partners like OneQubit, which is offering their solutions in Azure Quantum. There are many other CQC and all with whom we have announced partnership earlier this year. And we have recently announced with Toshiba, which will be offering the simulated bifurcation machine as well as an option. So I'm going to quickly jump into one of the example, right? This is illustration about traffic minimization. The aim is to reduce the different combination of routes that have been assigned to each car in the simulation. Now, this is an experiment which was done in Seattle along with Ford, where you see that there are different endpoints, right? And there are different cars which has been assigned. For this purpose, we have taken about 5,000 cars traveling from one or other location in Seattle at a rush hour on a Friday, right? And each car was given 10 different routes, options to choose from. Then the aim here was to minimize the congestion across the network, but also to minimize the average commute time for the people who are driving across, right? And on the left-hand side, as you could see here, this is the big red area, right? Essentially, this is where all the cars have chosen the fastest route offered to them, and you could see that it is incredibly congested, right? And many of these cars, the same routes, if it is following, then the darker red here, right? And our optimization algorithm started at this point, and within 26 seconds, running an unoptimized code on a Surface Book, we were able to reduce this overall congestion by 73%, right? And average commute time by 8%, right? So this is, of course, tunable and extensible as well, and depending on different types of scenarios. So other key areas where such kind of problem could be used is for flights, scheduling, logistics. One of the example which comes to my mind right away is Lufthansa, who's also leveraging this in their containers, especially in the aircrafts, which is carrying containers, right, and optimizing that scenarios. Now, there are other quick example which I wanted to highlight here is, this is the simulation which I wanted to show you, right? With the score coming in and optimization coming in with much better result with a quantum-inspired optimization. Now, moving ahead, I wanted to also give you some another example. So this is where we are using, the another aspect, right, which is with JIS and Shusho Corporation with Toyota, right, where we are looking at the frustrating waiting time, right, to and map it out with a waiting cost. Especially in this case, we are able to enable and express the problem in a special type of optimization problem, which is called polynomial unconstrained binomial optimization, in short, PUBO. So this is a type of problem where the variables can take two, or rather one of the two values, which is why it is called binary, right? And the goal of the optimizer is to find some combination of variables that minimizes the cost, right? And in the case of PUBO, right, each variable can interact with many other variables, as you could see here. So this is known as k-local interaction, and which basically increases the complexity. So this is especially an NP hard problem. Fortunately for us, we have Azure Quantum inspired optimizer, which is designed specifically to tackle this kind of PUBO problem. So in this case, when we work with JIS, we were able to use this to a great effect. In fact, working with Toyota Shusho and JIS, who used this Azure Quantum and Quantum Inspired Automation, we were able to achieve a 20% reduction in the waiting time for traffic conditions, right, over a conventional optimization method, which is great as well. So I would rather say that we are moving towards the closer, but I wanted to highlight that these are some of the very interesting, challenging problems, and I wanted to quickly highlight that there are other industries. Computational chemistry is huge scenario, and we are working very closely on this scenario, right, especially with Azure Quantum and INQ, Untitled Machine. Some of the industry like Dow has been using and working on it, and be able to look at the molecular energy of a ring of hydrogen atoms to be evaluated, and they're working on this scenario. This is very interesting use case as well. One of the other quick use case which I wanted to highlight is about finding the right material. So I'm sure all of you are aware of OLED's material, right? Especially organic LED. These are used in even monitors, the phones you are using today. Some of them smartphones have it, tablets, televisions, and computer monitors, as we know, right? Now, in this case, OTI Luminix has been working to use the computational chemistry to find the right material, right, to have the right design scenarios coming in, and they're leveraging this fast material finding approach using computational chemistry as well. Now, going to finance area, which is also huge. We know technology plays a key role in finance. So risk modeling, risk analysis, cybersecurity, credit scoring, underwriting risk. These are very interesting problems, and again, quantum inspired automation is actually working very is being used, and a lot of our customers and partners are actually using this today as well. So one of them, Willistar Watson, is closely working it's one of the leading advisory and broking solutions company, and closely working in to solve complex mathematical models to deliver great results for their client in risk modeling, especially turning risk into growth areas. Also, we have seen great implementation in healthcare and medical diagnostics. So this is one of the example where we have worked with Case Western Reserve University, where we were looking at optimizing the MRI pulse sequence for better quality imaging and faster diagnosis. And this is very interesting because it was also run on a classical computer, right? Simulation of a quantum computer on a classical computer, which basically is to enable the advance in the speed that could help doctors to detect diseases in an early stage. So, chemotherapy is very painful. And identifying if a chemo is going to work for a patient at a very early stage is challenging. So in this case, that the technology being used is magnetic resonance fingerprinting, which is a more sensitive scanning technique that could expect to detect whether a treatment of chemo would work or not in just one chemo, after just one chemo, right? Essentially, in this case, it's a data intensive pattern that is compared to a vast library of tissues with a known magnetic resonance fingerprint that can calculate a different directly from a physics simulation, and with sufficient precision, we could determine that a pattern match alone could be used to diagnose the colon or the brain cancer, or sparing patients from this painful invasive diagnostic procedures. So this is huge, and Microsoft has been working very closely with our partner in this case. Right now, going further, what has happened is that MRI scan were 3 times faster, and the results were also pretty accurate using this quantum-inspired optimization on classical compute. So with that, I would like to conclude here. Like, in the interest of time, I know we are jumping a minute ahead. What I wanted to very quickly mention is that there are many other applications. I just touched base on the surface of what can be done today, right? So there are many other things which can be done across automotive, governments are using this for city planning, public transport planning, and all. Manufacturing, energy is another one. So Dubai Energy has been working on this as well. I talked about some computational chemistry scenarios and so on. So there are many more use cases where we could look at. Now, whether you are learning quantum, or you're developing quantum algorithms or applications or applying quantum, right? Azure Quantum is an ecosystem, right, that opens access to the latest quantum innovation, and a lot of these are available. So I just wanted to highlight this. You can take go to these references. I've kind of for the help and the interest of time, I've shortened this out. So all of these are AKS link for you. You could go ahead and leverage. So we have done a lot of training materials have been added into Microsoft Learn and Katas for you to get started. At the same point of time, you could also leverage the training and workshops which has been delivered by our product team since July 2020. The last one in June 30, 2021. So these are very interesting, knowledge. You would be getting a lot of knowledge from looking at some of these sessions as well. So with that, thank you so much. I would conclude here, right, for listening and for your time. I hope you enjoyed this, and looking forward to your questions. Thank you.
Thank you so much, Ujjwal. That was one of the most informative sessions I've sat through, so I really appreciate you doing that and sharing your time. Look, conscious of time, so what we do, we've just got one question which I'm going to put up on the screen. I'm not sure if you can see it or not. So this is please talk something on interoperability of circuits on Python-based circuits, IBM, Qiskit, Google, Circ, and Q. So I'm just not sure if you can see that and you can answer that.
Yeah, so to give a very interesting, so that has been announced recently, and what it means is that people who are leveraging Qiskit or Circ from Google, they can directly write their code and use Azure Quantum to submit their scenarios or jobs to be solved using Azure Quantum as well, right? So the integration has been done. What I can do is probably share a link of how that can be. We have published this link on one of the Azure Quantum blog about leveraging Qiskit and Circ. So if you can just do a search, or maybe I'll post a link later after this is published.
Fantastic. All right, well, that concludes our session, ladies and gentlemen. I am incredibly grateful for your time, Ujjwal, and thank you to the audience. I wish you a very good end of your day or start of your day, wherever you're joining us from. And please join us for our next Reactor APAC session. We have one coming up on the 9th of December, focused on GitHub. So please join us then. And without further ado, I will end our session. Thank you very much, everyone.
Thank you. Thank you, everyone.
Thank you.